Okay, so I'm supposed to do number 13 and 16 point, that looks like B, and 16.4. Okay, and they want me to sketch the region we're integrating over, where the thing we're integrating, right, is from 0 to pi over 4, and from 0 to 1 over cosine theta of some function f of r and theta that I don't know, right, times r dr d theta. So let me identify some pieces, right? Okay, so what is this crap?
dA.
In area.
Yeah, that's dA, right? Which you could really kind of think about as dx dy, right? Cool. I'd prefer if you just thought about that as d area. Okay? But if you want to think about that as equivalent to dx dy, we're good. Cool? All right. What is this thing? This f in here?
Some function.
Just some function.
Yeah, that's some function that you're going to get the area underneath, or the volume underneath, right? Okay, so that's just some function. What's this guy? Oops, bad phrase.
R.
Sorry, this whole object. That's giving you the,
R value.
yeah, that's giving you the r bounds, right? You guys with me? So that's the r bounds. And what's this other one? That's theta bounds, right? Okay, so I'm going to start with drawing a plane, right? Which plane is this?
That's an XY plane, it looks like.
Probably the xy plane, although I don't actually know that.
Yeah.
You guys see that?
Okay.
I'm going to assume it's the xy plane. That might be a, no, you know what? I'm not going to label my axes. Take that.
Okay.
Okay. So, what do I know about the things I'm talking about? Where do the thetas live?
The theta is
Zero
zero
to
angle
pi
0
over
and angle 45 degrees.
So the thetas live between 0 and pi over 4, right?
Yeah. That whole slice.
Okay, so my angles live someplace in here. Keep in mind if the radius was negative, right?
Then it would be,
That would be kind of down over here, right? Like in this chunk. You guys with me on that?
That wouldn't be included if it was negative.
So if the r values were allowed to be negative, right? I maybe would be picking up some stuff down here. You guys see that?
That would be negative for everybody, right? Would that subtract from the rest of it?
It depends on the function, right? Let's not sweat that, because here my r bounds are positive, right? They start at 0 and go up to this 1 over the cosine of theta. Cosine of theta in this case is also positive, right? I do want to draw attention to the fact that you can write something like this and have it make sense here. You guys remember this? Like, you're allowed to integrate from 1 to minus 1. That's okay.
You get a negative sign usually, though.
Yeah, usually there's some sign flippage or something. But you are allowed to integrate over a region backwards. You guys all remember that? Calc 1? No?
Not two, but yeah.
Okay, so if you integrate from 1 to minus 1, some f of x dx, right? This is just minus the integral from minus 1 to 1 of f of x dx. Right, you're just counting this as your starting point and that as your end, so your interval gets counted backward. You guys all cool with that?
So I thought that when you use polar coordinates, r is just always positive.
Yeah, r is supposed to be
I mean,
positive.
it's defined as x squared plus y squared.
Yeah,
What's the square root of that?
but there's nothing stopping it from actually being negative. It's
I mean,
just a
just by
convention.
convention, when we talk polar, we kind of,
Yeah, so by convention, right, when you make these things, your r bounds should be positive. But it's possible that someone handed you one backwards, right? That
Yes.
they didn't adhere to the convention. Because of course the convention could be that r is minus the square root of x squared plus y squared. right? Like that would be a totally equivalent convention that you could
In a
use.
parallel universe, maybe that's how they do it.
Yeah, or parallel people, right?
Yeah,
Like,
I mean, just like every class, every math situation I've ever been in that where people use polar coordinates with by convention, R was defined as positive.
yeah. What I'm worried about is this is a function of theta, right? And if I dork this a little bit, like I wrote down the wrong function, I could easily end up with a negative value in there.
I see.
You guys cool with that?
Mhm.
Okay, so our R bounds, thankfully, are conventional R bounds, so they're positive. So all of this was over nothing. Where do the R's go from? They go from 0 to, what is that thing? Yeah, but that's hideous, don't do that. So, think that that thing means 0 is smaller than R is smaller than 1 over cosine theta, right? Okay, so this piece, right, that end, is at R equals 1 over cosine theta. Right, like a radius of 0 would be in here. And then someplace out here, there's whatever the heck that means. Right. You guys with me on that? Okay. So what am I looking to do? I'm looking to make that into something I know about. You could graph the secant function if you want.
Can't you see how big or small that function gets as your upper possible bound?
Yeah, you could try that. Like, you could try evaluating that thing when theta is 0, and then evaluate it again when theta is pi over 4, right? You could try evaluating it at a bunch of spots. Personally, I think it's probably easier just to,
Translate it into human Cartesian language.
yeah, multiply both sides by cosine theta, and then translate into usual language, right? So if I multiply both sides by cosine theta, I get r cosine theta is 1. What's r cosine theta? X? Oh. What does x is 1 look like? It's not radius 1, right? You guys see that? So your radii, right, range from 0 up to the graph of x is 1. Which is really telling you that r is cosine theta. Or, sorry, r is secant theta. You guys see that? So the region I'm integrating over is where? Yeah. Check done. Cool. Please note, now you should probably label your axes. I still don't know what the other one is. But that one I've decided to call.
You could assume the other one's probably y, but
Yeah.
our function is based off theta, not y, so.
Yeah, you guys see that?
And that is okay? Like to use x's and thetas? Or,
Oh, this other axis is definitely not thetas.
yeah, okay.
Right? This other axis is whatever the other thing you converted to polar with. So probably it's a y.
So this thing's still polar, it uses the x equals 1 as a way of evaluating how polar looks, or some.
So the integral that I'm dealing with is polar, right? The polar region I'm looking at is 0 is smaller than theta is smaller than pi over 4. And 0 is smaller than r is smaller than 1 over cosine theta. You guys with me on this?
Mhm.
But this thing here, right, tells me that I'm inside of what? Of x equals 1.
X equals 1. Between x equals 0 and x equals 1.
Yeah. That I'm left of x equals 1 anyway. You guys see that?
Yeah.
As it equals to though, couldn't it be right at x equals 1?
Yeah. So this part of x equals 1, but not all of it, right?
It has to
Because
be.
the other bit's restricted out because of the thetas.
Doesn't it have to include the edges in order to integrate based on, no?
Nah, integrals don't care whether you include the edges or not. So you could go through this whole thing and dot these edges, or you can go through and make them all solid, or you could go through and make this one solid and that one solid and leave the other one dotted. It doesn't actually matter. The volume doesn't care. You guys okay with that? Don't be. You should freak out about that, but that's true.
It's the change approach. The change of x approaches 0 there because it's so insignificant. So
Yeah, but the change in x approaches 0 everywhere, right? Because that's how I went from a Riemann sum to an integral.
what I'm
So I,
saying
like,
is just
cranked
adding
down on it.
one additional change of x. That's the only difference. I guess.
Yeah. Maybe think about it as that the volume under or over the top of this line has no width, right?
But didn't we define the Riemann sum based on a bounded, like in a 2D one or like a regular one, like on a bounded?
Yeah, it's a bounded interval that I chunked up into pieces, right? And usually it was convenient for me to say, oh, we'll take the left-hand endpoints, or oh, we'll take the right-hand endpoints.
So since they're infinitely small.
Yeah, it turns out it doesn't actually matter. If you like take midpoints or something, then you don't need either of the ends. And really, in a one-dimensional case, you're only talking about the area over a point and the area over another point. You guys see that? What's up, Kenna?
So where do you get the x equals 1?
So I got the x equals 1 from, I thought about what does it mean when r is 1 over cosine theta, right? So yeah, I was kind of testing the edge, because my bounds on my r go from r is 0, which is dot at the origin, up to whatever the heck r equals 1 over cosine theta means. So I just said, well, let me think about that. And so I thought about it a little bit, and I realized that I don't know what the heck this picture looks like. So I'll just multiply both sides by cosine theta and see what happens. And then I got this guy, r cosine theta, and I noticed from the conversions that this guy is an x.
Oh, okay.
Right, like when I convert to polar, there's that x is r cosine theta and y is r sine theta. And I just said, oh, hey, that guy looks familiar. It's kind of cheating, right?
So we only use the x as a way to evaluate the graph, not the function itself.
Yeah, this is really only me thinking, and it's only me thinking about the interval that about the area that I'm integrating over, right? So this goes from radii in between, for angles in between 0 to pi over 4, right? And those radii range from 0 out to this thing here, which is r times cosine theta equals 1. You guys see that? I really put the x in there for me. It has nothing actually to do with the problem. That is simply me thinking about how I converted and noticing that I do in fact know how to graph r cosine theta equals 1. Does that make better sense?
It's confusing having rectangular and then polar as well in there. That's why.
Yeah, I'm really thinking about back converting, right? Like normally I start with Cartesian stuff and convert to polar stuff. And on this one I wanted to draw a picture, and I'm not very good at drawing polar pictures. I'm better at drawing Cartesian pictures. So I kind of pulled it back into Cartesian land. You guys all cool with that? Okay. What? This?
Still not, Taylor, yeah. I'm still not 100% sure on where the r comes from in the dx dy to the dr d theta. If you're picking up another variable, but where does that really come from?
Oh, this guy?
No, the r on the far left. The r dr d theta. It'd be like getting an x dx dy almost if you went.
Yeah, so the issue is that d area, right? Little area blocks, right? When I take my plane and I chunk it up this way, these little things are all change in x by change in y, right? They're all the same everywhere. They're change in x by change in y. I didn't have to do that. I got to chunk this up in any way that made sense to me. So if I had made them a slightly different way, where I said, okay, I'm going to chunk up the plane, but I'm going to do it this way. I'm going to make all the same size slices this way. So these are all going to be changing y, y. But then when I cut up the x interval, I'm going to make them short over here. I'm going to make this first one change in x. But then I'll make this second one a little wider. And then I'll make this third one a little wider. Right? See how that would be weird, for one thing?
Yeah.
And then the change in area, one of these little boxes, right? It would depend on where I was sitting in the x direction. You guys all see that? That's exactly what happened with the polar cuts. Because in polar, I cut it up in little change in r slices, right? And then little change in theta guys like this. But these things get bigger the further away from 0 you get. So when you're putting a height to this thing, right? You're taking the area of the little rectangle you're over the top of and then multiplying by height to get the volume. But these ones seem to depend on where I am, how big that base is. That's the same thing that's going on with polar. Depending on how far out you went, that area, that base is bigger or smaller. Right? So that's what this guy's coming from. It's coming from that, it matters how far out you are to get the area of the base, and then you multiply by the height. And then we add all those up. Does that make better sense?
Yeah.
Kind of? Are you smiling and nodding at me right now?
No, I get it.
Okay.
I'm following.
Cool. Other questions on this?